So, welcome back, ladies and gentlemen. We will now start the proceedings of smart and autonomous shipping. While the previous session in here, in track A, was focused on various digitalization topics important to both manned and unmanned vessels, including ship-to-shore interactions, this session focuses more on technology directly related to autonomy and autonomous navigation. I'm very much looking forward to this session. May I first invite Ørnulf Rødseth, senior researcher at SINTEF Ocean, to give a speech on levels of autonomy for ships. Please go ahead, Ørnulf.
Hello, my name is Ørnulf Rødseth. I'm from SINTEF Ocean here in Trondheim, Norway, and I will present this paper on levels of autonomy for ships. There is some discussion whether we should at all talk about autonomy, and the car industry suggests to depreciate the term altogether and use driving automation or similar terms. Similar position has also been taken by CCNR, which represents parts of the inland waterway community here in Europe. However, if you look at what we are doing these days, we are actually transforming some of the operations that was done by crew, trained crew, into physical equipment. And we also want to approve that physical equipment to operate just as safe as the crew. And that poses some problems for us as the designers and researchers. So we think that you can define the difference between automation and autonomy as follows, saying that automatic is a process or equipment that under specified conditions can function without human control. That means it can do it, but it's not necessarily approved or fully designed to do it, while autonomy means that the same process or equipment under certain conditions is designed and verified to be controlled by automation without human assistance. And this captures, in our opinion, the central difference between what we talk about when you talk about autonomy versus automation. Going to the car sector again, these are relatively low value assets, and it's very difficult to see that they can be controlled by a remote control center or something like that. It's also a very complex traffic situation, and it's very difficult for humans to take over control if the automation fails. So basically, you probably have to go for full autonomy here if you want to go to a higher degree of automation. Then we have something we call industrial autonomous systems, which could be a metro or a light rail system. It could be an autonomous mining truck or something like that, or an autonomous ship. And these are high-value assets, and you probably want human supervision in any case, independent of the level of automation. There's also very high damage potential if something goes wrong. And this also points to the wish of having a human supervisor somewhere in the loop. And the environments are relatively controlled compared to the streets of the city. But there is still some complexity. And this opens up for a kind of cooperation between automation and human. Automation can take care of most, but humans can assist when automation fails. We do not believe that the ships will be fully autonomous, and this is exemplified by an encounter between an autonomous ship and a conventional ship. And there's a lot of operation that the automation system has to do to safely avoid the conventional ship. And there's also a lot of things that can go wrong. And here we will highlight two particular things, that the automation system has to predict what the other ship will do in a given situation, although you have people on board, and so you do not really know exactly what the ship will do. And also related to that is that the automation has to kind of make sense of any unexpected action by the other ship. And this will certainly be a possibility when you have people on board. Irregular action can be for a good reason, but it's very difficult for automation to understand it. And this again means that we are back to a situation where autonomous ships are a cooperative endeavor between humans and automation. And this also introduces a new paradigm in human automation interfaces for ships. There's a cooperation. Both can be in control, but only one at a time, of course. And if you want automation to be in control, it must also be trusted by the operator, otherwise it's useless. And this means, among other things, that automation must be able to detect and alert when human is needed, and also that the handover is safe and timely when control is transferred to the human. So time is central in defining what you could call a trusted autonomy. Here we have the collision scenario again, and you have the closest point of approach, which is too small for the automation system, and you know the time to CPA. This allows us to define two time constants, TDL, that's a response deadline, when something has to be done. And that's basically the same as the TCPA. But you also have TMR, which is the maximum response time for the crew. That's when the crew will be ready to act if you alert the crew to the situation. And this means basically that if TDL is larger than TMR, it's safe for the automation to continue operation. And it also allows us to define degrees of automation and control, as shown here. Just pointing out A1, partial automation. Automation is able to handle the situation for some time, but it doesn't know for how long. So it doesn't support this type of autonomy we are talking about. Constrained automation, on the other hand, here you know the time and you can compare it to TMR. For the humans' degree of control, it's worth noting C2, where the maximum response is 1 minute. And this is kind of typical for a remote control center where the operator is engaged with a number of ships and need to switch between them. And that could take a minute or two. C1 represents a situation where the crew is sleeping on board the ship during nighttime in good weather and good traffic conditions. And also here it will be possible to muster and get the crew back to the bridge in time to take actions if the TDL is larger than 20 minutes. These degrees can also be used to define classes of autonomy, as shown here, where you have fully autonomous in the corner, and operator exclusive, where the operator has to be there at all times. And then in between you have this AC area, where you have this constrained autonomy or autonomous control, where the automation is able to control the system and also knows for how long it can do it. Operator and automation cooperation is in the area where automation is able to control the system, but where the operator has to use own judgment to how long he can be away or she can be away. We propose to integrate all this into the operational envelope, which describes what the combined system can do, including both humans and automation. And this will partly be the general condition, that is the state space under which the system is safely operating. It's including the division of responsibility between humans and automation in this area, and also defining how system control tasks are executed in the different parts of the area. And finally, you also have to define fallback states for handling situations where the operational envelope is exceeded. These are very formal definitions that are quite useful in approval processes and design processes, but it may also be useful to have a kind of more human-readable definition of autonomy levels. And this has also been listed in the paper as a kind of logical combination of RCC and ship manning levels, as well as a level of automation. We also provide an example in the paper that you can have a look at if you like, showing how short sea transport from Rotterdam to Norway here in Europe could look in this setup. So to conclude, we still believe that autonomy is a useful concept, at least for ships, and that we should retain it, but with these more formal definitions we have proposed. We also pointed out that we will require a new type of cooperation between automation and human, which will have to be catered for in the new designs. We have pointed to the definition of the operational envelope as a more formal description of autonomous ship system capabilities. And we have also added some human readable levels of autonomy for those who want to do that. So thank you for your attention. If you want more information, feel free to contact me. And there's also some links here that you may be interested in having a look at. Thank you.
Thank you, Ørnulf. So I believe the floor is now open for questions to Ørnulf. Yes.
Hi, thank you very much. A very insightful presentation. I just wish to know that is there any lesson we can learn from dynamic positioning officers and their system? As you know, that one was implemented just only not too long ago, maybe 20 years ago. For the last 10 or years, very popular. Now it's common. And when initially implemented, those seafarers will know is so many challenges we call autonomous. Therefore, I just wish to seek is there any view, any lesson we can learn from there? Thank you.
The answer is yes, because I hear that operators of DP systems, they say that it's 99% boredom and 1% panic. And I think this illustrates this issue that automation should actually be able to warn people, the operator, in time for the operator to kind of understand what's going wrong and take the appropriate action. So I think DP is actually a very good example of automation that could have been designed a bit better with the operator more in mind. But that's my personal opinion. But anyway, the point is absolutely valid as you make.
Thank you, Ørnulf. Is there any other questions to him? There is also no questions from the online audience. So thank you very much, and we will move on then. Thank you.